Okay, so we started this unit talking about the parent exponential function, which looks like a function in the form f of x equals a to the x. Here we assume that a was a number that was more than 0 and was not equal to 1. Now, with that parent function, we had some properties that we are going to understand depending on the number a. Number 1, we know that this is going to represent an exponential growth model if a was greater than 1. And we understand this is an exponential decay model if a was bigger than 0 but less than 1. We know that all the parent exponential functions go through the point 0, 1, and they all have a horizontal asymptote of the y-axis. Today we need to move away from the parent function a little bit to talk about and use a more general exponential model that will cover a variety of situations. For reasons I can't tell you yet, because it involves calculus, the basic exponential model, it looks like f of t equals ce to the kt. Okay, or if you don't like using t's, we can say f of x equals ce to the kx. And here, c and k are constants. And it's going to be our job to determine what those constants are to match a certain situation. Okay, and the reason I have f of t as the basic model is because usually you want to talk about a situation where time is the independent variable. So x and t are basically the same thing here, but when you use t, you're usually saying that the independent variable is a time unit, either hours, minutes, or seconds. All right, we're going to jump into GeoGebra for a second so I can show you what's going on, and then we'll jump into a few examples. Okay, so here I have graphed a parent exponential function. It doesn't matter what the base is, but you can see that it goes through point 0, 1. It's an exponential growth model. Now let's suppose that we need our model to go through point E and point D, which are at 0, 2 and 4, 4. Okay, by manipulating the constants c and k, we can make this curve fit the data. And we won't do it exactly in this GeoGebra demonstration, but you'll get a feel for how we can get close by manipulating these two parameters, or what we call them. Right now, they're set to be 1 and 1, which means you're basically looking at a normal exponential function. Okay, so we know that changing the value of c, which is in front of the exponential function, will be a vertical stretch or a vertical shrink. Since I want the y-coordinate to be 2 instead of 1, I want to stretch this so that it goes through the point 0, 2. Okay, and that'll happen if I multiply the y value by 2, so that happens by changing the c to be 2. Now the k is found inside the function as part of the exponent, so this is going to be a horizontal stretch or horizontal shrink, depending on whether k is bigger than 1 or less than 1. Okay, so I'm going to mess with the slider bar for k until I can get the curve to also go through point D. And it looks like if I'm between 0.2 and 0.1, I'm in the ballpark. Okay, so I don't have the exact value. I can't do it here. I can mess around and try to guess what it is, but it's going to take some analysis and some algebra to actually get the right number. Okay, 0.175 is pretty close. Okay, but you can see we can manipulate these two parameters to get the right numbers that will make our exponential curve go through two given data points, and that's what we're going to do on paper. Okay, so here's the situation. It says, suppose I get 2 hours of sleep the night of May 5th, and we're going to call May 5th t equals 0. The next night, my amount of sleep triples. And one of the objectives for this lesson was to know what the buzzwords are for an exponential growth or decay model. Okay, and the buzzwords are the amount of something depends on the amount you had before, and it goes up a certain amount, okay, based on what you had before. So in this case, triples, the current amount depends on what my previous amount was, and in this case, times 3. And it could be decay also, where it gets smaller by a certain amount each time, a certain proportion. Cuts in half, cuts by thirds, etc. Okay, so assuming this pattern continues, write a function to model my sleep. All right, so first of all, let's determine what the variables are here. All right. Obviously, we're going to use t because t was given in the problem. So t will be measured in days. And then we need to choose a variable to stand for the hours of sleep. Okay, so we can use S for that if we like. We could use H for hours. Depends what your flavor is. Let's use S to stand for hours of sleep. Okay, so the next question is which depends on which. All right, clearly the amount of sleep depends on what day we're on. So I can create my function to look like S of t is going to be equal to some constant c times e to the k times t. Okay, here c and k are constants that we need to find out what they are to match this data. Now, what data do I have? I know that at time 0, the amount of sleep is 2 hours. May 6 would represent time 1. So 1 is the input, and I'm going to get 3 times as much sleep, so that gives me 6 hours. So now I need to make my function match that data. So in other words, I have to find the correct values of c and k that make it fit. So the easiest way to do that is to plug those two ordered pairs into this equation and see what I get out. Generally speaking, you're going to get a system of equations that you need to solve. So if I plug in 0 for t, I should get out 2 for s. So I'm going to get 2 equals c e to the k times 0. Now this is good news because k times 0 is 0 and e to the 0 is 1. So you get c times 1 equals 2, and therefore you have already got your value of c. All right, so that's a nice thing that happens. Not always, but in the case where you have the amount at time 0, you'll get the c. All right, so now we need to go ahead and figure out what the value of k is. So when I plug in 1 for t, I should get out 6 for s. So 6 equals, I now know what c is, so I can use 2 e to the k times 1. All right, and I need to solve this for k. Divide both sides by 2. So 3 equals e to the k. I need to get the k down. I can do that by using a log, and I'm going to use natural log. So the natural log of 3 is equal to the natural log of e to the k. K comes down in front, and the natural log of e is 1. So there's my value of k. So what does this mean? It means my function that models my sleep pattern will look like this. S of t equals 2e. Now watch how I write this, okay? Because this is kind of important. I don't want to confuse where the variable is and where the natural log is. Okay? I don't want to think that the t is part of the natural log. So I'm going to put the t in front of the ln3. So I can read that as t times the natural log of 3. If I put it after the ln3, I might get confused and think that it's part of the natural log when it's not. Now, there is another way to write this, and this is sometimes important for multiple choice tests or just for understanding how e is connected to something that triples. So look at what you can do with the exponent on e here. I can change t ln3 to ln of 3 to the t based on properties of logarithms. Now I have e to the ln of stuff, and I know that those two things cancel, so this could become 2 times 3 to the t. So those two functions are the same. I can't multiply the 2 and the 3, mind you, because that's violating order of operations, but you can see now that the 3 to the t would represent something that triples. You take your initial amount, which is 2, and every hour, or every day I should say, your amount of sleep would triple. Okay, so here's a graphical example now. We're asked, what is the equation for this curve? Obviously, it's an exponential curve, so it's going to fit our exponential model. And we can clearly see 2 points that the curve goes through. They're labeled point B and point D as 2, 1 and 4, 4. So I'm now going to go back to the x world and say that this is a function f of x, and it's going to be in an exponential form, so it's c e to the k x. And now I'm going to use the two ordered pairs that I can clearly see are on the curve, which are 2, 1, and 4, 4, to try to figure out what the constants C and K are. Okay, so when we plug in 2, I should get out 1. So I have 1 equals CE to the 2K. And when I plug in 4, I should get out 4. So 4 equals CE to the 4K. This is now a system of two equations with two unknowns, which are C and K. Now, when you solve a system, there are generally speaking only two ways to do that: substitution or elimination. And we're going to basically use substitution when we solve these type of systems because these aren't linear systems, which are set up for elimination. So what does substitution mean? Okay, substitution means solve for one of the variables, okay, in one of the equations, and then plug that into the other equation to get the other variable solved for. All right, so which equation do you want to use is up to you most of the time, and which variable you want to solve for is also up to you. So here's what I'm going to do. I'm going to take equation 1, and I'm going to solve this for C. Now, it's not going to be a number answer. It's going to be in terms of K, but that's why I have a second equation to use. Okay. So solve for C. What are we going to get? So we're going to divide both sides by e to the 2k. So C is equal to 1 over e to the 2k. I'm going to take that answer then and plug it into equation 2. And when I do that, I should get an equation that only has k's in it, and then I can solve for k, and then go back and solve for c after that. Okay, so let's see here. 4 equals, I'm going to replace the c with 1 over e to the 2k times e to the 4k. That's e to the 4k over 1 if I like. I can multiply these two fractions together. I would get e to the 4k over e to the 2k. That's equal to 4. And my properties of exponents or exponential functions, when I have the same base and I divide, I subtract the exponents. So that becomes e to the 2k. And there I go. Now I'm ready to solve for k, and I can go back and solve for c. So what am I going to do? I'm going to take the natural log of both sides. So I have the natural log of 4 is equal to the natural log of e to the 2k. The 2k is allowed to come down in front. I have the natural log of e, which is 1. And so now I divide both sides by 2, and I get the natural log of 4 divided by 2 is equal to k. And by the way, this could be rewritten, and probably should be rewritten, as 1/2 ln 4. The 1/2 then can go as an exponent on the 4 by the properties of logarithms. So this is really ln of 4 to the 1/2. And ln of 4 to the 1/2 is the ln of 2. Okay, so there's my k. Now we're going to go back and plug this back into the equation for c. So if I go back to the top, I think I had that c was equal to 1 over e to the 2k. So if k is ln 2, then c is going to be equal to 1 over e to the 2 ln 2. And 2 ln 2 is the same as ln of 2 squared, or ln 4. So I have 1 over e to the ln of 4, which comes out to be 1 over 4. So now let's go back up to the top here and see if this actually fits. So I would have y equals 1/4 e. What was my k again? My k was ln 4. Let's go back and check. I forgot already. Nope, my k was ln 2. Okay. So I would have, I'm going to put the x in front. Okay, x ln 2. Okay, let's go back and see if this actually works. So if I plug in a 2, I should get out a 1. So 1/4 times e to the 2 ln 2. 2 ln 2 is the same as ln of 4. E to the ln 4 is 4, and 4 times a fourth is 1. So far that's good. And then if I plug in a 4, I should get out a 4. E to the 4 ln 2 is the same as e to the ln 16, which is 16 times 1/4, which is 4. So it works.